Our next speaker doesn't need to be introduced. It's Bruce Momjian, a member of Postgres SQL community, and he will tell us about non-relational Postgres.
Privet, it's again wonderful to be here. My third day at the conference. Had a wonderful time last night. I hope all of you were here at the party. And I understand we have some kind of run tonight, but that's uncertain. But anyway, my name is Bruce Momjian. I'm from the United States. I have been working with Postgres for 23 years. I'm one of the core team members. I work for Enterprise DB. And this is one of my favorite talks because having worked with Postgres for so many years, I've seen a lot of growth, obviously here in Russia, but also around the world. And one of the primary reasons for that growth is not necessarily because Postgres is less expensive or also because it's open source, but another aspect is the innovation, the ability to handle workloads that traditional relational databases do not normally handle. And as you know, as we go into the web, as we do mobile, there are increasing demands for non-traditional workloads on relational systems. And this presentation highlights the 9 or 8 of those non-traditional workloads on relational systems. The other reason I'm happy to be presenting this here is something that may not be clear, and that is that the Russian development team, who has been with us since I started and to some extent before I started, here at Moscow State University over at the astronomy building, which I believe is that way. They were working on non-traditional workloads for relational systems. And a lot of the innovation that Postgres has come from our Russian team. Fyodor Sigayev is right there. He's one of the gentlemen. Yep, there he is. Oleg Bartunov, of course, Ivan Pechenko, Alexander Korotkov, all really stars of our team, and stars that are able to create software that really no one else in the world can create for us. So it's a mystery how it happens here, but I am very grateful. So let's get started. I talked about, I'm sorry, also I should mention that my slides are on this website right here, and of course recordings of other presentations and hundreds of blog entries also are there, okay? So I mentioned that traditional workloads for relational systems have been around for a long time. Specifically, 1970 is the year where relational systems really were defined by EF-COD. Now, of course, there wasn't a whole lot of relational systems in existence at that time. It took perhaps a decade or more for relational systems like Oracle and Ingress and DB2 to become popular. But the theory behind it really started in 1970, and 40 plus years later, okay, I guess this year would make it 50. I should probably update that slide, right? We still are using this technology, which is pretty amazing that you've gone for that long. But also, relational layouts are not always ideal. There are some workloads where a relational model really doesn't work. It's awkward, it requires a lot of coding, it's inefficient. So what I'm going to talk about in this presentation is to say that you can do relational workloads in Postgres, but also, primarily thanks to our Russian team here, you can do non-relational workloads in Postgres just as easily as you can relational workloads. And there's really no other relational system doing this. And I think it's one of the reasons that the Postgres has become so so popular. So again, I am so happy to be here. You know, the joke is that I'm so indebted to our Russian team. If they need me to come and flush a toilet, I'm on the plane. So whatever you guys need, I'm ready to help, because the community is so thankful for the work that's being done here. What is relational storage? Well, you might have studied it in college. It's the concept of rows and columns and tables, what you're familiar with. The concept of constraints, and also normalization. Normalization, you hear that a lot. What is normalization? Normalization, at least in its first form, is that each column contains atomic data, like a single value. You can't repeat things. If you have separate data, you create a separate table. So these are sort of the foundations of relational theory, and they work very well. They're very flexible. They allow for very complex data systems to be created. There's really no other system I know of. There are specialized systems for specific workloads, but in terms of general recording of data, it's hard to get a better system than this. However, there are some cases, and I'm going to go through 8 of them here in this talk, where the relational model really doesn't work well. And instead of trying to force the data that doesn't work well into a relational model, Postgres' approach, because it's extendable, okay, if you've ever heard of the extendability of Postgres, because it's extendable, we have the ability to effectively change Postgres to handle this non-relational data. Why is it inefficient? Well, query performance can be bad sometimes if you have non-relational data. Query complexity can be a problem if you try and store everything relationally and you don't have support for non-relational data stores as Postgres does. Storage inflexibility, storage overhead, and also indexing. That's something I'm going to be hammering on in part of this talk, is that not only do you have to have good data types to handle non-relational data, but it is critical that you have indexing that can also handle that non-relational data. If you don't have good indexing for those data types, it's a toy. It'll work for 1,000 rows, maybe 1,000,000 rows, but you're not going to throw hundreds of millions or billions of rows unless you have good indexing. And fortunately, again, thanks to the Russian team, we have very good indexing in Postgres, and it continues to improve. And you're going to see that in this presentation. So what are we going to talk about? I promised we're going to talk about 8 different non-relational data stores. We're going to start very simply and work to complex. But my goal from this presentation is that you come back and you say, you know, there's a lot of data that I want to store relationally. You know, personnel data, order data, tracking data, could be anything, products. But there's some of those data, whether it's geographic data, very detailed product data, where I just want to use something that's non-relational and mix it with my relational system. And this is where Postgres really shines. There are specialized data types for GIS. There are specialized data types for JSON. But there are very few systems which allow you to do relational and non-relational together at the same time. And I'm going to show that here. First, this is a data type called arrays. It's been around from the Berkeley days, which would be 1986, effectively. And we basically, to create an array, you basically take a data type, as we have here in red. Always look at the red on the screen, in the top. And what we do is we put brackets after it, like pretending it's an array. And what I'm doing here is I'm creating an employee table with the employee name and then some type of certification. Now, I could have created a separate table and joined to it and everything, but you know, it's just a certification, a list of certifications. I don't want to get complicated with it. I just want to put some data in the table, right? So what it allows me to do here, and I'm sorry I don't have a pointer that I can actually use on the screen, but effectively, if you'll notice the second line, I'm putting 3 different certifications in for that employee. Okay? Now, not only can you use it in this case, but even Postgres internally, if you look at the system tables, Postgres uses arrays to store things like permissions and function arguments. So not only are arrays useful for things like this, but even to store the system meta information in Postgres. We use arrays internally as part of the system tables. So you can take a look at the third query. We're actually listing the 3 array elements. And the last query is perhaps the most interesting. We're basically saying, give me the certification that contains a specific certification. Now, this is the first time we're going to see that operator, but that operator, the @ sign and the greater than sign, is something you're going to see over and over and over again in this presentation. And what it basically represents is the idea of containment. Does the field on the left contain the value on the right? Okay? Does the field on the left, the column on the left, which is an array, contain the value on the right? And we're going to see this for a whole bunch of different data types. But again, it's the sort of shorthand that makes it very easy for you to represent your request in SQL. You don't have to parse the array. You don't have to loop over the array. You merely use the operator and says, is this value inside of that array somewhere? And Postgres handles it for you. Also, just like my presentation yesterday, if you wish to run the SQL for this presentation, that URL there at the bottom, and again, that's in the slide deck as well, but that URL there at the bottom would allow you to run all the queries you're seeing today in PSQ. I'll just fly down on your screen. Okay. What else can we do? We can reference index into the array. So if I want the first element of the array, I would just say bracket 1. Okay. If I want to convert the array to rows, I can basically take the array values that are this way, and I make them basically rows. So an array which was 3 elements now becomes 3 rows. Okay. I can use unnest in this method. So I could say unnest, and I can now get what would look like a join, even though it isn't a join, but I've unnested it by using an aggregate. Okay. I can even convert an array. So here is 4 different rows from the system tables. And now what I'm doing here is I'm converting it into an array. So I'm taking 4 rows and I'm making an array out of it. Okay, so going the opposite direction. So that's all I wanted to talk about with arrays. Again, we have 7 more to go here. The second one I find to be incredibly useful, but also very subtle. And I'll explain why. When I used to work on relational systems in the 90s, we had a lot of data that had some type of temporal aspect. So when did the employee start? When did the employee leave, right? When did the client come? When did the client leave? So you had these start and stop times in your database. You probably all, those of you who have worked on relational systems, have seen databases that have a start and a stop time, right? Pretty standard. But you know, it's very hard to optimize a query that's doing start and stop, because you can create an index on the start column and an index on the stop column. But when you do a join and you say start is greater than this time and stop is less than that time, it's kind of hard. You have to look up all the records that have a start after the date and then all the records that have a stop before the date. And then you have to intersect those 2 together, right? You can't use a single index because you have to use the start and also the stop. Do you see what I'm saying? It's kind of hard because the 2 fields are separate. The system doesn't know they're related. It doesn't know one's less than the other, right? I thought that was as good as relational systems could get. But about 10 years ago, somebody thought of this idea of a range type. And somebody explained it to me, and they're like, well, it's like taking the start and stop column and putting them together. I'm like, okay, doesn't sound very exciting. But what made me excited once I understood it is because the 2 columns are together in one field, we can create a special index that understands those columns. So instead of having a separate index on the start and a separate index on the column, we can use bounding boxes or bounding ranges to actually narrow down the record that we're looking for in a much more efficient manner than we could if we had the start and stop in separate fields. Let me show you an example. So here is a car rental company, and you can see in the first entry, we create a data type. We use a data type called TS-TZ range. That sounds very awkward. But in fact, what it is a timestamp with time zone. Timestamp with time zone, you've probably used that, range, which means it's two timestamp with time zone fields together. It has a start, stop, same field. Second record, I am inserting a car rental. We have one car. I don't know, we have a rental car company that can only rent one car. Well, you get the idea, okay? And the first timestamp is the rental start. The second timestamp is a rental stop. And we use a specific syntax here. Even the bracket and the parenthesis have meaning in this syntax. One is exclusive, one is inclusive, okay? The third record is where it gets interesting. Do you remember the containment operator from the array entry? @ sign, greater than sign. What we're now saying is, give me the car rental that contains that timestamp with time zone. Kind of interesting, right? So give me the record that contains that timestamp with time zone, and in fact, it returns right away. The last query, I specified a timestamp that wasn't in the range, and I got no rows. So instead of having to say greater than this and less than that, I can actually just use that nice syntax right there. Now, you might say, oh, okay, so it's syntax, it makes it easier, my queries look better, okay? But this is where it starts to get interesting. I'm gonna put in, I think 3,000 car entries, okay? So for 10-year period, I'm gonna put in 1 day over that 10 years. So 365 times 10 is like 3,600. 3,650, something like that. And I can do a query in the second example. Give me the car rental, 2162, that contains that range, right? Just like before. We get it. And if I do explain down here, you can see that, unfortunately, when I'm looking for that entry, I'm doing a sequential scan. So I am reading all 3,600 records to find that one record. Now, 3,600 records, you're like, okay, that's not a big deal. What if I had 3.6 billion records? Okay, that would be bad. So, how do we fix that? Well, here's where the specialized indexing comes in to save us, okay? Special gist indexing, again, a lot of research done by the Russians here, allows us to create an index on that range type. And by doing that, I can now do an explain, and you now notice I am using a single index to pull out that car. Much, much faster than I could if I had separate start and stops. Make sense? And we're going to see this over and over again, where the data type is nice, the syntax is nice, it's nice to put them in the same field, but where things really start to take off is the idea of indexing this stuff. Another example with the range type, and you have to think about this one for a while. What if I don't want any conflicting ranges? I don't want any range to overlap any other range. This is a rental car company, right? We don't want to rent the car out to 2 people at the same time. Can't do that, right? So what you want to do is you want to try and avoid overlapping ranges. Now, how would you do that? Well, you could, when you're going to insert a new record in the car, you could check to see if there's an overlap, and then go to insert it, right? That would be the easy way to do it. But what if two people try and do that at the same time? They both look, they both don't see a record, and they both insert. You can't lock anything. You can't do select for update or something because there's nothing there. There's nothing to lock. There's a hole. So you'd have to do some kind of loop, and you'd have to update it and then read it back and make sure it was your record that got updated or something. Really bad, right? I mean, it's really kind of hard to do this in a concurrent system. What's really interesting about the range type is it has a special exclusion constraint, which I'm showing you at the top, and the two ampersands here on the right mean overlap. And by creating this index, I'm basically telling the system, do not allow overlapping ranges in this column. Now, I could make it much more sophisticated. I could do it by car number or location. We can get very fancy here. But here's a great example of something you really can't do easily from the client at all. It's not a question of making the query clearer. It's a question of, I don't know how to even do this in an inefficient way, okay? But here the system's taking care of it for us. It's preventing overlaps in our range. Really, really creative, I think, capability that, again, you would not typically see in other relational systems. Okay. Third one, geometry. This one you see a lot. I'm going to talk about a dartboard here, throwing darts at a dartboard. I mean, typically you would do this for some kind of GIS application where you had cars or people walking around or pigeons, I don't know, some kind of location service. But we're going to do this really simply with a dartboard. But you get the idea. If it was cars, it would be much bigger. If it was airplanes, it would be the same issue. So what I'm going to do is I'm going to take 1,000 darts and I'm going to randomly throw it at a dartboard. And I'm going to, randomly, like it's going to be all over the place. I'm a terrible dart thrower, let's say, okay? And if I take a look, here's the first 5 darts. And you can notice there's an X and a Y. Again, very similar to what we did with range types, where we have 2 fields that normally would be stored separately in a relational model, but we're putting them together. And we're putting them together for a reason, because we want to use those 2 fields together. So, you've seen the containment operator before. You probably haven't seen it written this way. This is, instead of @ greater, it's less than @. It's the opposite, okay? But that query is kind of interesting. It's saying, take the location and give me all of the darts that are within a circle radius of 4 from the center. Kind of nice. Hard to do kind of from an application. You'd have to make a box and at the client kind of measure. It's kind of cool. So I'm saying, figure it out. That red part there on the right is basically saying creating a circle. And say, give me the points that fall in that circle. Which is kind of nice. And we have 5 points, in fact, that fall in that circle. However, what we don't like is the fact that we're doing a sequential scan. So if I had thrown 1,000,000 darts, we'd have to look at all 1,000,000 points to find the place. Okay, not good. So we're going to create a gist index, very similar to the gist index we created with range types, right? And when we do the same query now with explain, you can see that that does an index scan. Okay, so instead of running through all the points trying to find all of them, it's actually able to use an R-tree index, which allows us to kind of bound what's going on. I know Footer worked on those range types long ago, but again, it works really, really well for sort of quickly finding points within a certain circle. Now you might say that's not enough. You might say, what if I want the 2 points that are closest to the center? Now, the classic argument here is I want the bar that's closest to my location. Everyone who does a talk about this typically is saying, I have a point, give me the closest bar to this point, or give me the 5 closest bars, right? Anyway, I'm not going to do that. We're going to do darts, but you get the idea. This is also, just as I said about range types, this is also a hard problem. Because even though you have this indexing and you can see, okay, give me all the points that are within 4, how do you know you're going to get 2 darts? Like, what if you make a circle of 4 and you only get 1 dart? Then you have to make the circle bigger, and then make sure you get at least 2 darts, and then make the circle bigger, and make sure you have 2 darts, right? So from your application, you're going to have to kind of play with this, and you're going to have to inefficiently make the circle bigger and bigger until you can get them together, okay? However, thanks to something called nearest neighbor search, what this effectively does is it walks through the index and finds the closest 2 points, and then returns those. It doesn't require your application to kind of make bigger and bigger circles until it finds enough points to process. Again, something that's fairly hard to do in the application, very easy to do in the database, because the database has the indexing, it has data types that understand these things, and it has very sophisticated capabilities. So again, when we're talking about using a relational system to be efficient, this is a great example, I think. Okay. And here's actually the example. I'm doing the limit 2 here. Well, this one is just the case where I'm giving my circle. This is the nearest neighbor. I'm sorry, I don't know why I did this. Here's with the limit 2, and we're basically saying, give me the 2 closest, and you can see it's actually using an index scan for that. So I'm sorry about that, but you get the idea, okay? Okay, XML. I'm going to kind of run through this really quickly. XML used to be really popular years ago. You don't see a whole lot about it anymore. But effectively, if you have XML data, Postgres understands how to use it. It understands how to iterate through it. So what we can do is copy a whole bunch of XML data in there. You can use XPath to find certain entries in the XML. You can convert them to arrays if you want. You can convert them to strings if you want. You get rid of the XML markup. You can basically sort them if you wish. You can do non-root queries. Here's a non-root query trying to find just some random rows in here. You can unnest them. Remember unnest we saw in the array record. We're going to do that again. Here's an interesting case. I want to find all of the drivers that begin with the letters HP. And it basically unnests them and then gives me the HP ones. Again, not super exciting. I'm just sort of letting you know that XML's out there in case you're doing stuff with it. What we see a lot more interest in is JSON. There are actually 2 different JSON types in Postgres. One is JSON and one is JSON-B. Both of them, a lot of research done and development done here in Russia for that. So JSON is basically a text field that is stored and validated as JSON. Here's an example of some random data I threw in there with JSON. I can pretty print the JSON. I can address it. This is the first time you've seen me actually go inside the JSON field, which is a single field that contains a whole JSON document. And I'm saying, give me the data value for the key, email, right? So again, this is a great example of us taking some non-relational data, specifically JSON, and accessing it inside of a relational query in a pretty natural way. So we're saying, yeah, in that data field, give me the email column, and I can see the emails right there. I can concatenate them together if I wish. I can do a query like this, so last name equals Banks. I can also use the containment operator. Remember the containment operator way back from arrays? So I can say, give me a JSON document that contains a key of last name with a value of Banks, right? I can create an index on it. Here I'm creating an expression index up at the top, and I'm indexing the last name. I can create, I can do IP address. I can even do aggregates on that JSON values. Okay, so I can do analysis of JSON. Again, using relational operators, kind of cool. Where things really get interesting with JSON, honestly, though, is JSON-B. Again, developed here in Russia. The JSON-B data type stores the the JSON values as binary. So there's a bunch of advantages to that. The native JSON, the JSON-B binary actually understands the JavaScript data types. So it understands a text, a number, a Boolean, a null, and sub-object data types for JSON. It indexes all the keys and all the values. So finding a specific key in a JSON-B document is very fast. We don't have to parse the JSON document. We've already parsed it when we stored it. We sorted the keys. We sorted the value very, very, very fast. The keys are, again, binary, are sorted, so we can do a binary search to look them up. There are some disadvantages. We don't preserve the order of the keys. We don't preserve white space. And we get rid of duplicates. So here's an example of a record where we're doing JSON. You can see there's a duplicate in there. We have the name, 2 keys that are identical. There's some white space here around the colon for age. If you convert that to a JSON-B document, you'll notice the duplicate is gone. There's only one name, the last one, and the space before the colon is gone. So again, just be aware, most people will be using JSON-B, but if you just want to bring documents in and out of Postgres, you don't want it to be changed at all. JSON is still a valid type, okay? So let's see what JSON-B can do. We're going to create the same type of table. We're going to create the same type of data. But now here at the bottom, we're going to do something different. We're going to index the entire JSON document. And this is where people get very excited, because normally in a relational system, you have to decide what you want to index. Which columns am I going to index, right? Indexes are big typically, right? However, with JSON-B, you can index the entire document, and any key or any value you want in that document, you can look up very quickly. It's kind of interesting. Okay, so what I see a lot of people do is they will create a table that has a fixed number of relational columns: product name, product cost, product ID, maybe manufacturer name, some pretty basic things that every product has. And then they put a JSON-B column at the end. So things like voltage, color, warranty, compatibility, certifications, things that like maybe only 3 products have a rating for pressure. Right, a pressure rating or a waterproof rating. Well, you don't want to have a column for every record that talks about pressure or waterproof. But what you can do is you can put all these unusual fields inside a JSON-B document. And therefore you have your fixed fields, which are relational. Pretty much everyone has them. You have constraints on them. You can join with them. And then you have this other JSON-B field, which contains all the stuff that really doesn't fit very well into a relational model. Really kind of interesting, I think. So by creating this GIN index on JSON-B, we can now query for the containment operator again there at the top. Last name is Banks. We use an index. In fact, it's this index right here. Okay? And we use the same index for first name Jane. Same index name down there. Okay? IP address, same index name down there. Okay? Really kind of interesting. So again, it gives people who want to do relational analysis a different option of sort of how to store their data. And this is really exciting for people. I know it doesn't excite maybe administrators that much, but for developers, having this flexibility, having a solid relational system like Postgres, and having the ability to be flexible like this, and very efficient in what they do, is really exciting. Years ago, people considered Postgres because it was cheaper or it was open source. Now there's some things you can only do in Postgres. You can't do them in other systems. 2 more types to go. The row type I want to talk about just briefly. It basically allows you to take several data types, columns, and put them inside of a single field, single column. So what I did is I created a type called driver's license, and I put 3 different fields in there. The state, US state, I'm sorry, in this case, an integer for the number of the license, and then a valid field. So effectively what I've done is for a truck driver, I've created a serial ID, his or her name, and then for the license, I didn't use text, I didn't use varchar, I used the type name that I defined initially. So when I go to insert Jimbo Biggins, I actually, in parentheses, have to specify 3 values: a state, a number, and a valid until date. So it's like a table inside of a table. Here's an example up here. You can see I'm selecting it. It comes out pretty much as I put it in. I can even do this. I can say inside of this license field, give me the state. So I'm going inside the license field, and I'm saying pick the state out of that and then tell me about it. Just be aware, if you do this, applications don't understand what they're getting returned. They just get this big string at the end. So don't use this too much. You see this a lot in triggers. If you've ever written a Postgres trigger, you see these record row types all the time because internally we can pass around this data really easily. Applications, it's a little harder. So let's talk about the last one I wanted to talk about, and this is a multi-layered kind of example, but it's probably the most common one, text fields. We all have applications, we all have databases that have text fields in them, okay? And when you think of a text field, you probably maybe didn't think of it to the same level that we have to think of it as a database. So you think of a text field, you're like, okay, well, it's an address, or it's somebody's name, or it's a document of some text, or maybe it's a bunch of UTF-8 characters, I don't know, okay? But you just think of it as a stream of bytes. But to use it efficiently for a database, there's different ways of looking at text strings. And depending on how you look at it, there's different ways you may want to process that data. And I'm going to explain that. I know it probably doesn't make a lot of sense right now, but let's walk through this, okay? So let's first start with loading some data in. So I got some fortune file from FreeBSD, and I copied a whole bunch of fortunes into Postgres, okay? So here's the first one. I'm looking for a line that equals the word underdog. And as you see, the first try, there actually isn't a line that has underdog, but there is one that's case sensitive. So if I use uppercase underdog, I actually get an underdog there. So I could do this query here, and if I want to query it and I don't want to worry about the case, I can do the lower, and therefore it works really well. However, what do I do when I do a sequential scan? Even if I create an index, the index doesn't work. Why doesn't the index work? Because I'm not comparing the column with a constant. I'm comparing a function call of the column with a constant. Okay? It's different. One's a column against the constant. One is a function call on the column of a constant. So unfortunately, I can't use the index I just defined, but I can do this. In Postgres, I can define an expression index, which says I'm going to have an expression, and I'm going to index the output of that expression. So now, if I use that same query here at the second query, it actually does use a proper index for underdog. Okay, it's kind of nice. So in this case, we're talking about a text string where you don't care about upper or lower case. Very, very simple. That's all we dealt with. Second example. What if I want a text string that begins with a word or a set of letters? So I want to know all the entries that begin with MOP. And I see I got two entries there. Okay, great. Not so great. I didn't use the index, right? So I'm going to have to go through all my records to find these. Ugh, that's terrible. So what I'm going to do is I'm going to create a special index here up at the top, and there's text explaining it. And I'm going to use a special operator. And when I do that, when I do my query MOP, now the system knows it can use an index scan on that. However, what if I want to do it case insensitive? So I want to find all the strings that begin with MOP, but I want to ignore the case of it. Well, it still doesn't work, because again, we have this problem where we indexed just the column, and we didn't index the function of the column. So as you may have guessed, we create a new index, lower of that, new operator, and in fact, that works. Okay? Now that's all kind of simplistic. We're just talking about the string, the text string as a string of bytes. But what if you want to think of the text string as a set of words? Right? And so instead of thinking it's just like, B-A-T space, byte, 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 byte. Now, I want to think of the string as a set of words. And I don't really care where the word is in the string, but I want to, so full text search, again, all from Russia. It allows us to do whole word, and word prefix searches, just like a full text search engine, okay? I can support and, or, and that. I can do not. I can do stemming. 21 languages supported. I can remove stop words. I can do synonyms. I can do transforms. So let's take a look at this. So if I do this in English, I can show how we supply a string, and it breaks it up into little words. Okay, so it becomes I and can get thrown away. Hardly the ly comes off, and the weight comes down. Or I could do something like this. It actually creates a nice little query for me. So I can say hardly wait, yes, softly wait, no. You can see it's comparing the text in red and making sure both of those words appear in the string above. Pretty straightforward. So let's create an index, and let's get interesting. So double @ sign, something we haven't seen before. We're basically saying, give me all of the strings that contain the word pandas, but also stem that word. So pandas becomes panda, and in fact, it finds a record there. Okay, great. And in fact, it uses an index for that, even better. So now instead of thinking of the string as a set of bytes, I can now think of the string as a set of words. I can do searches for words within the string. Normally, you'd have to use something like Solr or Elasticsearch or Sphinx to do this type of work. But here you're doing it inside the database, inside transactions. The indexes are remaining current. The data doesn't get inconsistent. Really very, very, very powerful, I think. Okay. Here's another example, cat and sleep. So I want the word cat and sleep to both to appear, and I have one sentence there. I can also do the second one. This is kind of getting interesting. I want cat and either the word sleep or the word nap, which cats are really good at both of those. So we actually now get two hits for cat and sleep or nap. And there's a way of doing this, like you would type it into a search engine on a website. That's a new capability. I didn't show it, but you don't have to use the @ sign and the pipe and everything. You can present it in a more normal way that people would do. Okay. Another example, what if I want to look at prefixes? I want to find all the words that begin with zip. I can actually specify it that way, and now it has returned all the entries that begin with the word zip. Okay. Here's another example. Yeah, and you can see that it actually uses an index for that, right? Because again, if it doesn't use an index, it's kind of useless to me, to most people, frankly. Okay. Final example. We talked about thinking of the string as a set of bytes. We talked about thinking of the string as a set of words. Now we're going to think of the string as combinations of letters. right? Remember, string of bytes, string of words. Now it's a string of a combination of letters. We have something called PG trigram. I'll show you in a minute. I say, give me all the words, all the entries that have the word varit somewhere in the string. You can see that, okay? But unfortunately, it uses a sequential scan. Boo. So what we're going to do, we're going to create an extension called PG trigram. Becomes part of Postgres, and we're going to create a gin index on that field. And now, when I go to look for the word varit, it actually uses that new trigram index. So it basically takes the whole string, breaks it up into 3-letter combinations, indexes them all, and allows you to look for those in an indexed way. Really, really cool. Here's another example using the zip. Give me the letters that begin with a zip using that syntax. So, you can see the index is used. And also you can do similarity searches if you want with Postgres and PG trigram. Give me the sentences that are similar to other sentences that I specify. And it uses an index. So these are the indexes I created as part of the text search document. Just in this section, all these indexes were created. And finally, these are all the containment operators that we saw, plus a couple more. But you can see containment for box, circle, text search query here at the bottom, and I think, and arrays, probably up there, in there, and JSON B, path. You get the point. So, really, really cool stuff. What you can do with Postgres, again, I think the value of it is that you can do really flexible things. My warning to you, in closing, don't use these non-relational things too much, because if you do, you're going to end up looking like this animal, okay? The data starts to spill out all over the place, and the data gets very confusing. So I think these features are really great, but make sure you use them when you need them, not necessarily everywhere, because your data could become a mess if you're not careful. So that's why I think mixing relational with these non-relational data types where appropriate is the wisest choice. Thank you very much. I am out of time. I will be here for the rest of the day.